Hello, my name is Tom Boving. I'm a professor of hydrogeology. I'm studying water in the subsurface, groundwater, and I'm studying how the water moves and how much water we can pump from wells. But I'm also studying groundwater quality, meaning is water polluted? Is it fit for human consumption? What can we do about it if it's not? Are there technologies that can clean up contaminants and pollution? And lastly, I'm also working in developing countries like India on supplying clean drinking water or irrigation water to rural villages. You can never approach hydrology in isolation just by focusing on one particular issue. It's always more than that. Surface water, groundwater is connected. What happens in a nearby well affects my well at home. What happens a mile away on a polluted site can potentially impact my aquifer at home, my groundwater at home. So students need to understand that hydrology is a science that encompasses many, many other sciences and other fields. I also want my students to have an international perspective, realizing that water use, water availability in our part of the world is a given. Nobody thinks twice about opening the faucet and expects clean water, and that's how it is, and that's a great thing. But in places like India or other places around the world, that's absolutely not the case. The study of water hydrology is relevant for this generation and next generations in the context of changing climates, in context of sea level rise. It is important that we understand the limitations and the fact that groundwater is a finite resource. We need to understand that we need to take care of this resource. We need to understand that we have to have the understanding that allows us to take care of the resource. So the take-home message is that water is critical for us right now and will be more critical for the foreseeable future. And we need engaged minds, young minds, to address these issues and ensure that the water is available for future generations to come.
Good morning, everyone. My name is Karen Lapointe, and on behalf of the URI Foundation and Alumni Engagement, I'd like to welcome you to our program today. We are happy to present the third and final presentation in our Spring Faculty Office Hours series, which has been dedicated to the topic of clean water. And today we welcome from India, Thomas Boving, Ph.D., Professor of Civil and Environmental Engineering and Geosciences. Acting as moderator of the discussion is Mary Beth Riley-McGreen, a digital content strategist in URI's Department of External Relations and Communications. If you have questions for Professor Boving, please post them in the Q&A section on your screens, and we'll do our best to get to as many questions as we can. And just a note, today's program is being recorded. In a few days, you'll receive an email with a link to the recording, along with recommended resources for further reading. You'll also be receiving a very brief survey from us, and we welcome your feedback. And now one final note. We are delighted that Professor Boving is joining us from India, and we have our fingers crossed that the connection and sound quality will remain stable throughout this presentation. So if you see us shifting a little bit throughout the presentation, you'll know that we've had to make some changes, but I think it should be fine. So now what I'd like to do is invite Mary Beth to join me on screen and to introduce Professor Boving.
Thank you so much, Karen. Welcome, everyone. I'm so happy to be here and so glad you could join us today. As Karen mentioned, this semester, the Faculty Office Hours series is devoted to a single topic, clean water. At URI, two initiatives, Water for the World and Water E2S2, which stands for Water, Engineering, Economic, Science, and Society, are dedicated to its study, calling access to clean water the defining issue of this century. Today, I'm pleased to introduce you to Professor Thomas Boving, who is joining us from India. He is a professor of civil and environmental engineering and geosciences in the College of Engineering and the College of the Environment and Life Sciences. Professor Boving's research interests include environmental engineering, hydrogeology, water treatment, and groundwater remediation. He received a Fulbright Nehru Academic and Professional Excellence Award, which is enabling him to spend this semester teaching and conducting research at the Indian Institute of Technology, Roorkee. Professor Boving also works extensively on research in Indonesia and here in Rhode Island. He earned a Ph.D. in Hydrology and Water Resources Management from the University of Arizona and an MS in Geology from the University of Tübingen, Germany. And now, I'd like to invite Professor Boving to join me on screen for today's presentation.
Thank you, Mary Beth, for the introduction, and thank you everyone for joining us today. I hope the sound quality is acceptable. I'm currently in India, and hopefully you enjoy my talk. Let me bring up my presentation, and then we can talk about water. Apologies. Okay, sorry about that. I hope everybody can see my slide. I titled my presentation Water, the Defining Resource for Our Century, because I'm convinced that addressing water quality and water quantity issues will be the most important challenge of our lifetime, but certainly during the lifetime of our children. Fortunately, at URI, we have many faculty members in various colleges who are studying water in all its different forms. Recognizing the huge potential a few years ago, we started an initiative called Water E2S2, as Mary Beth introduced already. That stands for Engineering, Economics, Science, and Society. The idea was that Water E2S2 brings together experts from all of URI, from all colleges, and encourage a multidisciplinary conversation about water. And over the last few weeks, you have already heard from my colleagues in the Civil Environment Engineering Department, Dr. Binka Craver and Joe Woodwell, about their work in the Water Quality Lab, in the Water for World Lab. So today, I would like to highlight some of the expertise in the Geoscience Department. And I will start with Dr. Sodiprada Nang, who's a watershed hydrologist and biochemist. She studies hydrogeology and is a water quality modeler. We also have, since last year, Dr. Chris Rossignello and Dr. Ambarish Kamalka in our department. Chris is a groundwater resiliency expert under changing climate conditions, and he studies coastal hydrology as well as Arctic hydrology. Dr. Ambarish Kamalka interest is in global and regional climate change, climate dynamics, and climate modeling, and is related to water. And Mary Beth already introduced my interests, which lie in environmental hydrology, sustainable water treatment, emerging contaminants, and coastal hydrology. Again, Mary Beth has done a great job introducing me, so I keep this very short. I was born and raised in Germany. You can probably tell from my awful accent. And I spent about half of my life in Germany. I got my master's or diploma, as we say in Germany, from the University of Tübingen in Germany. Then I worked for 3 years as a consultant in Germany. And then I started my Ph.D. research in hydrology at the University of Arizona in Tucson. And right after graduation, I started in Rhode Island at the University of Rhode Island, and I have been at the university ever since. I've studied extensively on groundwater issues, and I co-authored the leading textbook in our field named Contaminant Hydrology. Well, you may ask, why did I stay in the US? Why didn't I return home? The short answer is US universities are still the best universities in the world. I say still because other countries are catching up rapidly. I'm seeing it here in India, I've seen it in other places in the world, but we are still the best. So that enticed me to stay in the US. I had a plan B in case my university career didn't work out. I, as a little child, was already fascinated with cowboys. So I figured if I go and stay in the US, I could become a cowboy. As you see in this slide here, I was probably 4 to 5 years old when I made that decision. Didn't come to it. I'm still a hydrologist, but never bad to have a plan B. Well, as long as I can think, I've been fascinated by water. Back as a child, I loved to build dams along small creeks in a nearby forest. And this went on until the forester came and chased us away because we flooded the entire area. So I decided not to do that again. As a teenager, I started looking at water more from the scientific perspective, first using electricity to split water into hydrogen and oxygen, and then getting a kick out of it when burning up the hydrogen to create water again. I like to think that I invented the hydrogen economy, but of course that is a whole different story. Now, later, I decided to study hydrology because I realized that water is likely to replace fossil fuels as the most important resource of mankind. That conclusion was rather obvious to me because, unlike oil, we cannot find a substitute for water. Without water, there is no life. All living things depend on water, need water. Also, water shapes our planet. It has done so since the earliest days of Earth, some 4 billion years ago. It still does today. Think about the Grand Canyon, which would not exist without the waters of the Colorado River cutting deep, deep into the rock. So today, under conditions of a changing climate, we often have too much water or not enough. We have seen this play out in California this year, where the landscape was first suffering from severe drought conditions, and then turned into large inland seas in some areas due to extreme flooding. What is even more important to me is the effect of human activities on water quality. In many places around the world, water resources are polluted with industrial chemicals and untreated sewage. While here in the US, we have managed to clean up our environment to quite a bit over the past decades, clean rivers and safe groundwater now is a distant memory for many people in much of Asia and Africa. What else motivates me? You might have heard about this number before. 2 billion people have no or limited access to water. 2 billion people, that's almost every third person on the planet. In a minute, I will talk about India in particular, but let me share that over the past 2 decades, I've been working in developing countries like Nepal, Jordan, Kenya, and Indonesia. And during the many visits to these countries, I was able to observe firsthand how rampant environmental degradation of water resources in both urban and rural areas is, and how it has impacted the lives, in particular, the lives of the poorest people. I sincerely hope that my research on water issues is contributing to a better future of people most affected by limited access to safe water. If I can just help a few of the billions of people, I would be more than happy. So this is really what drives me. Now, I got very lucky, and as Meredith already stated in the introduction, I received a Fulbright and Arrow scholarship to conduct some of my studies in India at the Indian Institute of Technology in Roorkee. This institute is India's oldest and most prestigious civil engineering school. It was founded in 1847 to train engineers for the British Raj. At that time, British engineers built a gigantic network of irrigation channels in India. Even today, these channels exist and distribute water from the Ganges River, from the Ganga, over wide swaths of land, allowing for a massive expansion of agriculture in the Ganga plain over the last 150 years. This is a true industrial marvel, and one of the really good things that are still in existence today. Now, I will be in India till mid-May, and during this time, I have an opportunity to work with very smart students and very smart faculty on emerging contaminants. More about that later, but first let me introduce you to my temporary home in India. If you're not familiar with India, Roorkee is located about a 4-hour car ride away from Delhi. It's located at the foothills of the Himalaya and near the holy cities of Haridwar and Rishikesh. The latter, Rishikesh, being famous as the world's yoga capital. And for those of you who are Beatles fans, probably remember that this is the place where the Beatles found an ashram in the 60s. Very beautiful place, absolutely amazing. And what you see here are the pictures of the IT campus, the old historical building built by the British. And down here you see the Solini Aqueduct, which is is part of that gigantic Ganga Canal system that the British built in 1846. In this picture, which I haven't taken myself because ever since I came to Roorkee, the air pollution is so severe that the visibility is limited to a few miles. But I was told on a clear day, you can see the Himalayas from Roorkee. In the background, about 180 miles away, are the chains of the main Himalaya mountains. I'm hoping before I leave to get to see this for myself, but like I said, so far that has not been the case. Now, talking about the Himalayas, these are often referred to as Asia's water towers. And this is because the Himalayas are covered by the largest body of snow and the highest concentration of glaciers outside the polar regions. The runoff from the Himalayas ensures the water supply for over 1 billion people. The Himalayas feed Asia's greatest rivers, including the Ganga, which you can see here. The red dot is Roorkee, the Ganga, the Indus River, and also the Brahmaputra River. Together, these three rivers form what is called the Indo-Gangetic Basin, or IGB. This is home of almost 1 billion people, and again, a very fertile place to conduct agriculture. Now, the headwaters of all these rivers get fed by monsoon rains and melting glacial ice. The future, however, of the Himalaya is severely threatened by climate change because the glaciers in those mountains are melting, just like most glaciers do worldwide. According to some estimates, it will be only a few decades before the flow of meltwater in the Ganges basin will be dropping dramatically, which will have serious consequences for the region's water supply, as you can imagine. Excuse me. Currently, however, there's plenty of water available for agriculture in the Indus-Ganges basin, where about 70–90% of irrigation is satisfied from groundwater resources. And interestingly, groundwater resources are fairly stable in this area, which is good news, unlike places like the Ogallala Aquifer in the US and other places in southern India where groundwater tables are declining rapidly. Also, in and around big cities like New Delhi or Lahore, or the capital of Bangladesh, Dhaka, groundwater levels are decreasing fairly rapidly because of overpumping. And this has significant effects for the future of the people living in these areas, because there's currently no substitute for the water. Take a look at this amazing slide. This is a 14th century step well. It's called Agasan Kibaoli step well. It is in what is New Delhi now. It was built in the 14th century. And if you look carefully, you can still see the water, the groundwater at the bottom of this well. So in the old days, people came down here, deep stairs down to the water to collect water and bring it home for whatever uses. Many of these step wells still exist in the Delhi area, but they're no longer used. And that's the problem with water quality in particular. This well is particularly famous because it's featured in many Bollywood movies. So if you're a fan of Bollywood movies, you may have seen this place before. So the contamination that causes all these problems with groundwater comes from multiple sources. And most of India's water, 70%, is contaminated with raw sewage, industrial effluent, agricultural runoff. And interestingly, only 1/3 of all the runoff actually receives treatment. That means 2/3 of all the sewage goes directly into the rivers untreated. As a result of pollution, about 200,000 people die every year from waterborne diseases in India. That's a huge number, 200,000 people. Besides industrial and agricultural runoff pollution problems, there is another source of pollution, arsenic, which is a natural contaminant and is present in about 30% of the Indo-Gangetic plain. And same is for salinity. Salinity and arsenic can be naturally occurring, but also enter the groundwater due to human action. And together, the salinity and arsenic make large swaths of the groundwater unusable. And then there's another pollution issue that is related to emerging contaminants, which are chemicals or materials we know very little about their distribution and impact on the environment. Information about these contaminants is emerging. That's why we call them emerging contaminants. One important example of emerging contaminants are pharmaceuticals. India is the world's third largest manufacturer of pharmaceuticals, and there's mounting evidence that high concentration of pharmaceuticals are present in effluent entering India's rivers and groundwater. Take a look at this slide here. This graph shows one particular compound. It's called trimethoprim. It's an antibiotic. I'm showing here the concentrations in the Yamuna River. The Yamuna is the river that flows through Delhi and then on to Agra, home of the Taj Mahal. So trimethoprim is a widely used antibiotic and it's an emerging contaminant. In India, it's available without prescription. My host at Indian Institute of Technology has shown that the concentration of this compound in the Yamuna River are actually the highest reported concentration in surface water anywhere in the world. We're talking micrograms of this compound being consumed if one would drink the water. So the problem is on many levels. We have industrial contaminants, we have sewage, we have emerging contaminants. So what should we expect from safe water? What makes water safe? So there are basically three criteria. Water is safe if it's free of bacteria and viruses. It needs to be free of particulates. Particulates is what makes water cloudy, suspended solids. And it should be free of inorganic and organic compounds and precursors. So basically three very simple criteria. Question is, how do we get there? Now, in our home, the US, we have very complex, also expensive drinking water treatment and sewage water treatment plants. They do a great job removing most of these contaminants. However, and unfortunately, these very expensive technologies are out of reach of most developing communities in rural areas. So the question is, what can we do? It will only be a time until India has increased the number of water treatment facilities and drinking water treatment units, but the way there is still long. So what we need are bridge technologies. And these are unconventional water treatment systems that can be sustained by local communities and can deliver improved water until a permanent, more effective water supply solution becomes available. Now, a bridge technology must be acceptable by local communities. It's very important to have technologies that local communities can identify as beneficial and useful. One such technology is Riverbank Filtration, which is a very simple technology. You may not even want to call it a technology because all we do is we take advantage of naturally occurring water treatment mechanisms. So think about the river being polluted with whatever you can think of. If we can force the river water to flow through the sediments that surround the river and make the water move to a well, we can remove a lot of contaminants by simple natural processes like absorption and chemical reactions. This is what the old Egyptians already knew 5,000 years ago. Here's a quote from Exodus 7:24 saying that the Egyptians dug wells around the rivers to drink, so because they couldn't drink the water, it was polluted already in those days. So many of my projects are focused on riverbank filtration technology. And this picture probably tells the whole story. We have the water from the river here untreated, and here's the water from our riverbank filtration well. What you cannot see is that this water is free of pollutants, free of bacteria, and is actually drinkable. I drank it myself. So it works quite well. Now, I've been working in India since 2006, and I've visited the country about 30 times. My work could have not been possible if it hadn't been for my collaboration with TERI, which is the Energy and Resources Institute of India, one of the leading NGOs. And in particular, Ms. Kavita Patil, who can be seen here. We have been collaborating along 5 major rivers in India, installing riverbank filtration systems. And those pictures here give you some impressions of what that work entails. So after drilling well, we're installing pumps, we're laying pipelines to water tanks where villagers then can collect clean drinking water. We ensure that the water is clean by testing, by very extensive testing before we even supply the water, and make sure that the water is indeed usable and is not laced with harmful chemicals. We also spend a lot of time educating the local population. You can barely see Ms. Patil here, but she's talking to villagers in the school of the small village, and she's explaining to them how riverbank filtration works and what needs to get done to maintain it at the local level. This is another example of a very simple technology. It's a Biosand Filter. It was also implemented as a collaboration of URI with TERI in a small village called Nursa in the western Ghats of India. It's basically, as this little mural here explains, a technology that mimics riverbank filtration. We're basically recreating the conditions that exist along our rivers, but we do so in what is a concrete box that is receiving water from some pre-filters which remove leaves and regulate flow. Here you have maybe a better impression about what I'm talking about. In the foreground, you see my 2 students, Miles Schelling and Ian O'Hara, and explaining to our guests from local villages how the system works. And this is before we fill the system with the sand and before we start moving water through it. And I must say, this was an absolutely amazing experience for me, working with these very, very engaged students from URI who actually stayed in the village for 3 months, living basically with the villagers, ensuring that the system gets built to the right technical specifications. So these are just 2 examples of simple technologies. There are others like created wetlands and whatnot, but I don't have the time. But let me at least tell you what we were able to learn from our tests. So we were able to show that these simple low-cost bridge technologies can indeed serve rural villages with clean water. We have shown that E. coli bacteria, which is a measure of pathogens in the water, can be reduced 2 or 3 orders of magnitude. That means 99.9% of all the bacteria can be removed with these technologies. And we found that the number of self-reported chronic diarrhea cases due to the consumption of polluted water declined from 21% to almost 0. So very effective. We also have shown that the system can be operated and maintained by local talent. And by that I mean by people who sometimes only have a 4th grade education and have no technical or engineering training at all. But we are able to train the people to the degree that they can feel comfortable with running the system. Also, we established that there is a willingness to pay for clean water, and this is extremely important because without some financial incentive in the system and money in the bank, systems fail, and they need to have villages need to have financial resources to, let's say, fix a broken pump or fix a broken pipeline. So villagers are in general see the value of clean water. We also found that women-led systems are typically more successful than systems where a male is in charge. And this is something that other projects have also found. And so we make it a point to put at least half of our technical and financial people in charge who are women. Now, it is
I said this earlier, crucially important that we engage our students in our studies. The students need to get out of the classroom and into the field and apply what they have learned. And this is a multicultural and multidisciplinary experience because they are faced with living in remote villages under very harsh conditions, not just using their hydrology knowledge, but they need to use many other sciences, chemistry, biology, social science to make a project a success. And I would advocate making international experience like this one a mandatory part of a university curriculum. And I can say at URI, we actually do already have such experiences. It's called the J-term. For example, the J-term Indonesia, which I lead, is a 2-week trip to Indonesia that we offer every year in January. It focuses on water, marine pollution, biodiversity, and geology. This is a picture from our trip last January, where we visited Bali and other places. This tends to be such an important experience from our students that many of them changed their career trajectory. Some became Fulbright recipients, some joined the Peace Corps, and quite a few got employed by international NGOs, now working on issues like water, pollution, and biodiversity. So this J-term is a really great addition to the URI curriculum, and I'm very blessed to be able to lead this class, and I'm looking forward to next January when we go again to Indonesia. With that, I'd like to thank you for your attention. There's much more to say. For those of you who wonder what this picture is about, it's the Ganga River in Rishikesh, and Shiva, who is closely related to the origin of Ganga, is right here. So that's all I have for today, and now I'd like to invite Mary Beth back to join me on the screen.
Thank you, Professor Boving. Sorry for the lag there. I have a lot of questions. I'm going to work backwards, actually. You mentioned that women-led systems you've found have been more successful, and I don't know how comfortable you are with positing the why of that, but I'm really curious to hear what your hypotheses may be around that. Does it have to do with children and motherhood? I'm curious about that.
Yeah, that's a very good point. And I don't know if an ultimate answer, but from our experience, we've seen that women tend to put greater value into clean water because they're realizing that polluted water makes the children sick. Many of them die. And so they know the value of water. They know that it's actually good to invest into technologies like the ones I've talked about, because their children benefit. Their children are less sick. They can go to school longer. They're not staying home with stomach aches. The women themselves benefit from clean water because it becomes closer available to home. So instead of walking long distances to a river, the water tanks are in the middle of the village. So the time spent on fetching water is significantly reduced, which helps them to be more efficient at home and do chores more quickly. And again, it boils down to the children having more time to assist children doing their homework. So this is what we have observed, what women in the villages have told us, that it's all about children, that they recognize the value of the water. And I don't want to go into why men are maybe not quite as qualified, but you get the message. So we make it a point to put women in charge, and that has worked very well for us.
Okay, I have a question here from Phil Smith that's kind of in the same wheelhouse. During my own trips to India, I too found immense need for water resources and mitigation of contaminated sites. While the locals were all for action, the powers that be seem more interested in their own power. I guess it's more of a statement than a question, but maybe you might want to say something to Phil's observations.
Yeah, like in many developing countries, there's rampant corruption. There are bureaucracy, levels of bureaucracy that make it very difficult to make changes, in our case, to the water infrastructure. It seems that when you work at the local level, things are possible.
Mhm.
As soon as you involve even lower level politicians, it gets very complicated. However, I must say things have changed in India over the last 15, 20 years I'm coming here. There's much more, much less corruption today because there's an active fight against corrupt politicians, corrupt. And this is changing. This is changing and has a benefit. It's created a lot of advantages for the rural population, the poor people who suffered the most in this corrupt system. So I'm fairly hopeful that in the coming future, this will get better and allows us to do more of these projects that I just talked about.
Mm-hmm. You mentioned harsh conditions that, part of J-term, part of one of the learning opportunities, in addition to academic study, is the lived experience. Could you tell us a little bit about your living conditions in India right now, so we can get a sense of what you're experiencing in terms of, water availability, the heat, what that, how communities conduct themselves under harsh conditions like you described?
Well, at the moment, I'm pretty blessed because I'm living in the dormitory of the university.
Mhm.
It's air conditioned, which is a blessing because it's 103 degrees outside. But when we are in the field, that's not the case. And I mentioned Miles, Mike Schelling, my student, former master's student, who was absolutely amazing. He lived in the villages. He ate the local food. He slept on what is a very hard mattress in a house with no electricity, no running water. So he got up in the morning to fetch water for the tea that he was cooking on a makeshift gas stove. And when I was younger, I went through a similar experience in Nepal, where we stayed 2 months in the jungle of Nepal, mapping a completely unknown area for geology purposes. You have to have the right mindset to live in an environment like that. It is certainly challenging in the beginning, but once you get used to it, it's such an experience. It is truly something that it's hard to describe, but it prepares you for life in general. As a young student, I became much more resilient, much more, I trusted myself more, simply because I went through these hardships, through these experiences. And I think for our generation, the young generation, most of our students are so, how can I say, spoiled, maybe not the right word, but for them to see how much of the world lives not having access to, you don't just open the faucet here, you have to go to the next well or to our filter and obtain water. You need to plant your food in the rice paddies. If the crop fails, you may not have anything to eat. So it's important for our students to see how much of the rest of the world lives. And this is an experience that you cannot teach in the classroom. This means we need to take our students out in the field. And for 2 weeks, everybody can survive 2 weeks. And our students come back and they tell stories at home, what they did, what they achieved. They're proud of themselves. And like I said, it enables them to explore new opportunities. Go work in the Peace Corps, become a Fulbright student, go out there, work for an NGO, do something. So yes, I think harsh conditions are a good thing.
Yes. Phil just followed up with something else that I'll read to you. I agree that the next generation of Indian scientists is improving the process, lots of distance to cover. And could you speak about site mitigation, such as the chromate processing in Tamil Nadu impacting groundwater?
Okay, very specific question. However, let me start saying that I'm absolutely impressed by the quality of the students and the quality of the faculty. In fact, some of the equipment that is present here at my host university is something I don't even have access to on your URI campus. So very advanced, very sophisticated equipment and facilities. Okay, this is one of the elite schools, but I've seen this in other places around the world. That's why I was saying earlier, the US universities are still the leading universities, but we need to ensure and invest more into our infrastructure to keep up with places like India. Now, having said that, Indian scientists are fully capable to find solutions for the many problems they have. I'm finding that my knowledge that I bring to my host institution certainly is appreciated, and there are certain things that I can bring to the table, but there's also things I can learn from my colleagues, and I'm impressed by where they are, how far they have come over the last 20 years that I'm coming to India. So I have great hope for the future that these many pressing issues like the Tamil Nadu issue that I'm not particularly familiar with can be resolved using local talent, homegrown talent. And was just in the news today, India has surpassed China in the number of people. There are more people in India now than in other countries. That's a huge potential. And if India plays its cards right, educates its young people, they can change the world. So I'm very hopeful.
Mm-hmm. Part of what we've done in arranging this series is tried to choose faculty, URI faculty who are working, on the international stage, but also very locally, to kind of illustrate that water is a resource that we all have to be, as you said in your opening video, we all have to be thinking about taking care of this resource. We all have to be stewards of the water supply. And we are seeing now, of course, in California in particular, crises that are not going to be easily solved. And California, I understand, is now resorting to groundwater use, which I understand once you do that, it can be hundreds to thousands of years for the earth to replenish that groundwater. So not a good solution. Very close to home, we have Block Island, and I know you've done some research and work on the island. Could you talk about the island's particular water challenges and the work that you're doing there?
Yeah, sure. So you don't have to go to India to face water challenges. I think that's where you're heading. And here at home, we're facing our own challenges. I mean, in my presentation, I said we cleaned up most of our rivers. You can now swim again in the Blackstone, and you can fish and this and that. That's over decades of work. So we're able to address many of the really obvious problems, the pollution problems. What we're facing now is pollution that comes to us from the ocean, meaning we're seeing salt water intruding in our coastal aquifers. That means by pumping groundwater in areas like, let's say, the South Coast and Block Island, we'll be taking out more water in some instances than is naturally replenished. So if you take out more fresh water, you're creating space for the salt water to move into. And this is a process we call saltwater intrusion. It's a normal process. It is reversible if one stops extracting more groundwater than is being naturally recharged. The problem is that we living in a society where everybody is on their own, fights for their own, and people maybe don't even have the understanding that their action can have these negative impacts. So let's say if you have a well in, let's say, Charlestown or in Block Island, and you have a big pool or a lot of visitors, and there's a lot of water being pumped from your well, you could end up in a situation that your well becomes salty simply because it's too close to the coast. You pumped out all the groundwater, or much of it, and that water that's remaining mixes with salt water. So what you're creating is basically water that is too salty for human use. Maybe you can use it for cooking spaghetti, but definitely not for making a nice cup of coffee. Mm-hmm. So this is what we're looking into. My students, PhD students, master students, we have field sites where we install wells, where we're measuring what is the water quality. Does it change over the year? Does it change during droughts? Does it change after storm events? And what we're finding in some areas, there are first signs of saltwater encroaching on our freshwater. And it's by no means a done deal, and this can be reversed this early in the game. But we need to be aware that this is another problem that we're facing, the encroachment of saltwater into our coastal aquifers. Yeah, that's what I'm doing in Rhode Island, besides other things. But I think in the future, and I haven't even talked about sea level rise, which will accelerate this phenomenon, of course, but just the fact that we overstressing our coastal aquifers could lead to problems in the future.
Mm-hmm. Your colleague, Professor Craver, talked about her work in the context of humanitarian engineering, and I know this is something very important to you too. And when I use that term, I'm talking about, and please correct me if I'm not being not talking broadly enough, but it includes respecting and incorporating indigenous knowledge into solutions that you design for your work in other countries. But what occurs to me right now is that whether it's Block Island or California, there's a behavioral component to all this that transcends culture, namely that in order to reverse things, we're going to have to change our habits and attitudes towards water, perhaps, which I imagine is probably harder than installing, in some ways is harder than installing a filtration system. How have you noticed any in your time in India, have you noticed your own attitude toward water changing because of being so close to the work and so embedded in a different part of the world where water is not, as you put in the video, just a matter of turning on the tap and making assumptions about the water you're drinking?
Yes, absolutely. I mean, the value of clean water is so tremendous. I mean, I being a hydrogeologist, I'm biased. Of course, I know about water quality, but being raised in the developing world, first in Germany, then later living in the US, we're so used to having fresh, clean drinking water. It's just, we take it for granted, right? I mean, we don't think twice about it. The only time when we maybe think about it, if we go south of the border in, 2 weeks in some country, we may think about it. Then we can't go home and forget again and open our faucet and all is good. Now, during my time here in India, this is different, right? I mean, I in the evening, I, for example, make sure I have cooked water next to my bed. So when I wake up at night, I have fresh water that I trust. If I don't cook the water, I can wake up with diarrhea the next morning. It's what it is, right?
Mm.
Now, I try to avoid plastic bottles, so I could easily run to the next store and buy a 10-gallon jar of 1 liter jar of water. But by doing so every day, I would accumulate a great amount of plastic.
Mm-hmm.
And that's something I'm not prepared to. So for me, that means I have to sacrifice some, what's the word? Convenience to not pollute the world by additional water bottles. And that means I have to go and cook the water, make sure it cools down so I have it readily available when I need it. These are small little things, right? And when we travel with our students, we actually make them account for all the plastic they use.
Oh, wow.
So in the end, it's an eye-opener for them. They have 10, 20, 30 empty plastic bottles that they produce and throw into the local garbage. The problem with garbage, and that's a whole different subject, in countries like India, is that it has nowhere to go. So it often ends up right next to the road or thrown into a river, and then ultimately ends up at the beaches or in the oceans. I can't even tell you what happens here when the monsoon kicks in. All this junk that is accumulating, plastic and whatever, in the ditches gets washed out and away into the Ganga River. The Ganga River becomes basically a big conveyor belt for plastic debris and any garbage you can think of. And that eventually gets into the Bay of Bengal and then goes all the way around the world. I mean, it's just, I don't know where to start and where to stop. But in a world like this, it's not just water, it's many issues. And I try to focus on what I do best, and that's water. But for our students, there's so much to do here. And I think that this is a real opportunity for our students to put what they have learned at URI into reality and then see they can have an impact by taking their engineering skills, by taking their chemistry skills, by taking whatever skills they have to good use in solving, addressing some of these very, very pressing problems.
I was one that image that you conjured of the Ganges with after a monsoon, that sounds heartbreaking. And that thought led me to another thing that you said in the presentation, that 2 billion people around the world have little to no access to safe and clean water. And correct me if I'm wrong, but 200,000 people die annually in India because of waterborne disease.
Mm-hmm.
Being in this discipline that you are doing, the work that you do, do you, and you did kind of answer this, but I guess I'd like you to explore it a little bit further. You still feel hopeful for the world and the
Yes.
preservation of water. Where do you derive your hope from?
Well, I look at the young minds that I'm seeing, not just in India, but also at home. Our children are so engaged. They see the world with the same eyes that we are. And I'm really have to give it to our children. They don't despair. Most of them don't despair. There's certainly some, right? But they see this as their challenge. They may complain that we left them with this mess, but they're ready to take on the problems. And they're innovative. They look for new ways. They look for changes in the way they live their lives, which can reduce some of these problems that we have created. So I'm hopeful because I look into the eyes of these kids, and I have 3 kids of my own. One just graduated from URI, the ocean engineering department. One will be graduating in May, public health. So I know that we should be hopeful because we have these great young minds. And again, there are technologies out there, bridge technologies, that will allow us to make a difference for those communities who are hardest hit, or the poorest communities, by giving them access to simple, low-cost solutions. Humanitarian engineering, as Dr. Kramer said, is a very valuable discipline in engineering, which I think we should encourage more students to think about how to put their knowledge to use for humanity, and not go for the highest paying job, but for the job that is, in my case, most fulfilling. I mean, I love my job. I don't even call it a job. It's probably a calling. So yes, I'm hopeful. That's the bottom line.
From Michael Vivaldi, just a comment to Professor Boving. I am a URI graduate of wildlife biology in 1994. In the last few years, I also have stopped purchasing single-use plastic containers unless it's an emergency situation. Thank you for all the great work, Professor Boving.
Oh, thank you so much.
That's very nice. And for myself, I'm glad that, you know, maybe you in retirement, you might go to Plan B in the cowboy's life. I am very, very happy that you are here at URI and doing the work that you do. So thank you. Thank you all for joining us today. As mentioned, within the next few days, you will receive an email with a link to today's recording, along with a few recommendations from Professor Boving for further reading and listening. This concludes our Faculty Office Hour series for the spring semester. We hope that you'll join us again this fall when we'll be exploring the arts with professors from the music, theater, and fine arts departments. Thank you again and enjoy the rest of your day. Thank you again, Professor Boving.
Thank you so much. Thank you, everybody.